Welcome to video 3.4 on the periodic table. So in this video, we're just going to look at the periodic table and understand how it's organized. We're also going to look at how these chemicals were arranged on the periodic table and how it was arranged according to their important chemical and physical properties. We've already learned about the periodic table, so some of this might be reviewed, but it's just going to take things a step deeper and also add a few more facts and tidbits. So here are some vocabulary terms. Again, anytime, pause the video, search them, but you should be able to figure them out in context or as I define them along the way. So the periodic table, as we talked about originally, the periodic table is nothing but a big cheat sheet. And it's a cheat sheet that has tons of data and information collected to help young scientists and even veteran scientists accomplish learning and accomplish experiments quickly by getting the information they need easily at their fingertips. So the original periodic table was created by a Russian professor. He was a college professor and he was helping his students try to understand and try to learn these elements. And so he came up with what you see on your screen here as the first periodic table. Notice his periodic table looks a little different than ours. And when he did his, he actually arranged them not by the atomic number, but he arranged them by their atomic mass. And at that time, there was about 60 elements discovered, which was, again, in 1869 when he created this, which happens to be the first year the great University of Purdue University was established. But in 1869, while Purdue was getting built in West Lafayette and opened its doors, over in Russia, I think Moscow to be exact, Russian chemist Dmitry Mendeleev came up with this periodic table, ordered it by their atomic mass, but again started to line them up based upon their properties. And this is where the beginning of the periodic law came into effect. So periodic law now is known as our ability to arrange the elements by their atomic number. And when we arrange it by their atomic number, we see certain similar trends or commonalities between those elements. So again, I'll give you a good working definition of periodic law. It's when the elements arranged in order of their atomic number show the periodic variations of their atomic structure and most of their properties. So the idea is arrange them by their atomic number and we're going to see their chemical trends or their physical property and physical trends line up. So today's periodic table looks like this. Now today, you've already learned our periodic table is lined up by the atomic number. Atomic number is just another way of saying the number of protons an atom has, or an element has in this case. Today we have 118 elements that are made up of things that are very common and very rare. They're made up of things that are found naturally in the world, and they're made up of things that are man-made. And so the reality is we have 118 elements now, but that number could increase in the future. But right now we work with 118 elements. They are arranged by their atomic number, but then they are also organized by their electron configuration. As you've already learned, we have the S block, the P block, and the D block. So when we want to organize this, we also came up with some other terms on how we can describe the different rows and columns in our periodic table. So the first thing you've already learned is that the rows from the left to the right are called the periods. You can see here that our periodic table has 7 periods. So a period is a row from left to right, and our columns, the up and downs, are called groups, or they can also be called the families. So again, the families or the groups, all the elements in the same group of families are organized that way because they share similar properties. And that is a key part to the periodic law, that these groups are arranged because all these elements, lithium, sodium, potassium, they share very similar chemical properties. And we're starting to learn now also that they have similar chemical properties because they have the same number of valence electrons. And so as we get started here, let me talk about valence electrons. Valence electrons, as you heard in the previous video, are just the electrons in the outermost energy level that are in the S and the P orbitals. Let me say that again. The valence electrons are the electrons in the highest energy level that are in the S and the P orbitals. So an easy way to look at this is look at the noble gas configuration on your periodic table, and then look at all the electrons in the S and P orbitals after the noble gas and the noble gas notation. So you can see here that lithium has 1 valence electron, beryllium has 2 valence electrons. When I jump over to the P block, boron has 3 valence electrons, carbon has 4 valence electrons, all the way up to neon who has 8 valence electrons. So we already told you that the valence electrons could be between 1 and 8. And here's an example. Lithium has 1 valence electron, neon has 8. Sodium has 1 valence electron, argon has 8. And so this idea of 8 valence electrons actually created up another rule, which I will show you in the next video. But that rule is called the octet rule. So an octopus has 8 legs, right? So the octet rule is this rule that when elements exist, they would prefer to have 8 valence electrons in their outermost shell. In other words, they want their s orbitals and their p orbitals filled. So this is what you're going to see, that fluorine has 7 valence electrons. Well, if he wants 8 valence electrons to obey the octet rule, fluorine is going to look for an electron to steal, and that's why fluorine is often not neutral, but fluorine is often negative, and that's called fluoride ion. Lithium's the same way. Lithium has 1 electron in that s block. So for lithium to obey the octet rule or to have a full outer shell, lithium will often give up an electron to become like helium in its configuration, but that's why lithium becomes plus. So we'll show up more of that in the next video, but I just want to give you the idea of the octet rule because I will refer to it a little bit in this video. And so like I said, the group 1, again, on your periodic table is labeled right here, group 1 or family 1. When you call it the family, you label it as the alkali metal. So this is something you need to know to be educated, that group 1 is called the alkali metals. These metals are soft, but yet they're still metals. And they are super, super reactive, and they will combine very easily with other nonmetals, especially halogens. And what you see here is that the group 1 all have 1 valence electron, like I just mentioned. They all have 1 valence electron because they all end in that s orbital with just 1 electron. And that's, again, what I have here in your notes. They all end with the s orbital. Moving along, we see our D block. Our D block is called the transition metals. Again, on your periodic table I gave you, it is found right here. This is your D block. Your D block are the most common metals that you see. These are called the transition elements or the transition metals. These are good conductors of electricity. And normally, these guys will fill up with their they'll fill up with their s orbital and then begin to fill up their d orbital. But as you've seen in the last video, sometimes we come up against exceptions to where instead of having 3s2 and then filling up our 48, nickel would rather do this, than this. So this is common that it would fill up the 3s2 and then fill up the 4d. But like I said, every now and then, things like chromium, things like silver will have exceptions where they will actually fill up the d orbitals first, or even put 1 electron in the d orbital before they move on. Again, those exceptions can all be found right here. But just keep an eye out. Transition metals do have some variations in electron configuration, but normally they do fill up like this, with the s orbital get filled first and the d orbital get filled second. Next, we get our lanthanides and actinides series. These guys are very rare earth metals, and they also consist of man-made elements. They are found down here on the bottom of the periodic table. They're called the F-block elements. And then next, we look at our P-block elements. These properties are not very similar. The P-block includes both metals and nonmetals and metalloids. So because of that stair step that falls down there to split between the metals, nonmetals, and metalloids, we see the P block has very different characteristics from being metal to a nonmetal, but yet they still have the same valence electrons. And so when they go to bonding, they still form similar types of bond, and they also form similar types of ions. So again, this is my P block. Remember, your P block has valence electrons that count up the P electrons, but the P block also adds in the S electrons. So when you look at fluorine, fluorine does not have 1, 2, 3, 4, 5 valence electrons, but instead fluorine has 7, 1, 2, 3, 4, 5, 6, 7 valence electrons. All right, so we're moving right along. Again, these are just things that you're going to pick up in the reading, things that you're just learning, and I'm just kind of going through it to help you and assist you in hearing these details for the test. Group 17 is called the halogen family. Halogen family, again, is group 17. Halogen family is the most reactive elements or nonmetals that we have. Why are they so reactive? Because again, it goes back to this idea of the octet rule. All these guys have 7 valence electrons. And the octet rule says they want to be like the noble gases. They want to be stable. They want 8 valence electrons in their outer shell. So since these guys naturally have 7, they're going to be super reactive on the hunt, looking for an extra electron to steal so that they can have a full octet. And when they steal that extra electron, these guys will form a negative charge. So again, these are the most reactive nonmetals. They all contain 7 valence electrons. And finally, we see the noble gases. This is the last name I want you guys to really know. The noble gases, they are the group 18. These guys are highly unreactive. Some other words you will hear when we say unreactive, we'll say the word inert, or we'll even say they are very stable. Inert, again, stable just means they don't react. They are content the way they are. They have their 8 electrons, so they obey the octet rule, and these guys exist as gases. And again, on the periodic table, the noble gases are here in group 18. Helium, it's a little bit of the debate whether or not he's a noble gas. He's definitely a noble gas, but again, sometimes whether or not you want to consider him part of family 18 depends on if you want to throw him over here in the group 2. I go ahead and call helium a noble gas. I go ahead and say he's part of group 18, but sometimes you can argue that he is in group 2, but he is definitely not an alkaline earth metal, which is the name of the group 2. Last thing I'm going to point out to you guys is this other unique trend that we have going on. When we look out in nature, we see these different elements exist. And sometimes elements, for whatever reason, and it has to do with how reactive they are, but also how abundant they are, they do not exist by themselves as an individual atom. So if you're walking out in the woods and you see a hydrogen atom laying on the ground, you're not really going to see just one hydrogen atom sitting there. But hydrogen is going to bond with himself to create what's called a diatomic. Remember, di means 2, atomic means atom, so a 2-atom element. There are 7 diatomics you need to memorize. You need to memorize these because it's going to come up again and again where when we talk about these elements, they're not going to behave as individual atoms or elements, but instead they're going to exist as this molecule. Instead of an individual atom, individual element, they're going to be a molecule where they just simply bond with themselves. And so here are your 7 diatomics. There's 2 ways to memorize this. One way you can memorize this is by remembering the phrase honk, the breath. If you memorize the phrase honk the breath, you might want to write this down. Honk the breath. It reminds you that hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, fluorine are your diatomics. That in nature, they do not exist as individual atoms, but they exist as a molecule bonded to themselves. The other way you can memorize these 7 diatomics is look at your periodic table. If you look, Hunklabrith includes chlorine over to fluorine down to iodine. And so on your periodic table, nitrogen over fluorine, they form a 7. And so there's 7, 1, 2, 3, 4, 5, 6. So it forms a 7, and then the other one is hydrogen over here by himself. So another way to remember Hunklabrith or the 7 diatomics is you can, if you want, outline or shade this in and make a number 7 here. And those are the 7 diatomics you need to memorize with this 7 here that they make in the periodic table, but plus hydrogen. And so again, that's the video. Periodic table is very well organized. It's very intentional in the way it's organized, and it's organized in a specific pattern. This is that periodic law idea that it's organized by pattern to show its properties. And the properties of elements are common among their groups. So if an element's in the same group, it's going to have very, very similar properties, very, very similar reactivity, and exactly the same number of valence electrons. And then different groups of different elements contain different properties. That's why the noble gases are very stable, and the halogens and the alkali metals are very reactive. Have a great day.